Hello everyone, I welcome you all to this lecture series on Industry 4.0. Today we will be discussing the cyber physical systems. Cyber physical systems are considered the backbone of Internet of Things as well as Industry 4.0. But before learning what is actually a cyber physical systems, it is important to learn what is an embedded system. So let us first discuss what is an embedded system. So as written here, information systems which are embedded into physical devices are called embedded systems. These embedded systems are found in telecommunication, automation and transport systems, among many others. So lately a new term has surfaced, the cyber physical systems. This actually distinguishes between the microprocessor based embedded systems and more complex information processing systems that actually integrate with the environment. A precise definition of cyber physical systems or CPS is that they are integrations of computation, networking and physical processes. Embedded computers and network monitors, they control the physical processes with feedback loops for physical processes affect computations and vice versa. I'll now show you some examples of these embedded systems. You can see here there are a few examples. Here this is a embedded system for a washing machine. Similarly here you can find there is a development board. So these are actually some of the examples of embedded systems. While the first embedded system that you see here is not having any connectivity, it is having a interface that through which the user can give some inputs, and then you have this development board on this side which is also an embedded system which has got some connectivity. You can also use it to control some particular devices. Apart from having the controlling operations, it can also connect to the Wi-Fi, through which it can even connect to the internet. We can understand cyber physical systems in this way, that these are embedded systems having some connectivity. So the figure here shows the basic block diagram of a cyber physical system. It in fact shows what are the different components of a cyber physical system. So the different blocks are like this: sensing and actuation component. So here we have the different sensors and actuators. So sensors means, let's say, temperature sensor, humidity sensor. These are some examples. Actuation means, let's say, a washing machine. So if you are allowing water inside the washing machine, then there is a certain valve actually that is controlling the water's inlet. So that is also one of the examples of actuators. So these sensors and actuators are connected to an embedded system. Then the second is interfaces with humans. In this embedded system you can see that there is an interface that can actually communicate with the humans. The humans can actually give commands to the cyber physical system through this interface. Then the next is the control components. So here we have the particular algorithms which are responsible for controlling the different actuators based on the sensor inputs and the inputs provided by humans. Besides that, you can see there is a block called information processing and communication components. So this block is actually responsible for processing the information captured from different sensors and also the inputs obtained from the humans. It can also send the data that has been captured to a cloud or to some location, to a remote computer through the internet. So now we can easily discuss what is basically a cyber physical system. So as the definition here says, a cyber physical system can be just about anything that has integrated computation, networking and physical processes. A human operator is a cyber physical system, and so is a smart factory. So this actually shows a block diagram of a cyber physical system. So what we are essentially doing is we are controlling this physical equipment with, as you can see, cyber, that means internet. Through the internet or through connectivity we are controlling some physical equipment or physical processes. So these cyber physical systems enable the virtual digital world of computers and software to merge through interaction, process management and feedback control with the physical analog world, thus leading to an Internet of Things, data and services. One example of cyber physical system is an intelligent manufacturing line, where the machine can perform many work processes by communicating with components, and sometimes even the products they are in the process of making. An embedded system is a computation system embedded within a physical system. The emphasis is on the computational component. Therefore, we can think of all cyber physical systems as containing embedded systems, but cyber physical systems emphasis is on communication and physical as well as the computational domains. So now you can easily correlate this definition with this given diagram. Now that we have learned what is a cyber physical system, let us now look into critical cyber physical systems with embedded processes for Industry 4.0. That means in Industry 4.0, what are the different processes that will be controlled by the cyber physical systems? As you can see in this particular diagram, there are different kind of processes that will be controlled using the cyber physical systems. So there are devices and buildings. So if we consider the civil engineering related areas such as flyovers, bridges, buildings, all these require some sort of cyber physical systems for the structural monitoring. This is basically the application. Similarly, coordination of processes. Different processes are running in the industry, so there is a need of coordination. Cyber physical systems are quite capable of coordinating the different processes. Similarly, transport routes. These transport routes are a major part of the supply chain, and even cyber physical systems can be used to optimize them. Many logistic processes can also be optimized using the cyber physical systems, and they can be controlled. Similarly, medical processes can be also controlled using the cyber physical systems. So these are the different processes that we can think of being controlled by cyber physical systems. So let's say that we have a system which is controlled by embedded system in a particular industry, and then we would like to implement cyber physical systems so as to basically integrate that particular piece of machinery with the Industry 4.0. Then what are the different ways we can do it? So this implementation or this conversion of any normal embedded system to Industry 4.0 can happen through these three kind of methods. An interface to the internet or a similar network is necessary to extend an embedded system, which is usually made of control units, sensors and actuators, to a cyber physical system. Which means that if we want to convert any embedded system to a cyber physical system, then apart from the control units, sensors, actuators that are present on the embedded system, we have to have an interface to connect it to internet. Now, in order to achieve this, there are various approaches that have been investigated in the context of this development, and some of the basic approaches are these three. First one is the direct system extension. Second is the system expansion by microcontroller board. Third is the extension by smart sensors and actuators, obviously. So let us learn one by one. So this is the first kind of system, which is the implementation of CPS using the direct system extension. So in this individualized solution variant, the embedded system, if not available yet, is extended by a communication interface to access the internet, and the software is changed accordingly to enable communication over the internet. Example with the cloud. So as you can see here, a system exists, an embedded system or an industrial system exists, which is having a control unit, the different actuators, sensors, etc., and they are all connected through the field bus. Some of the examples of field bus can be RS485 Modbus or the CAN bus that is quite used in the automotive industries. Okay, so we can add a simple module, okay, which is written as system extension here, which will connect to the cloud via the internet. So to this end, all the sensor signals of the system must be transmitted by the control unit to the cloud. Methods should be implemented to control the actuators via internet. So this figure actually shows the arrangement by which we can implement this thing. So next is system extension by microcontroller board. So in this solution variant, a microcontroller board that has the various communication interfaces such as CAN, UART, WLAN, Ethernet, etc. is developed. So this is connected to the embedded system and takes over the communication to the internet or a cloud. However, this requires uniform interfaces over which the board can be connected to the embedded system. The software of the board must be adjusted separately to each system. However, the entire code need not be rewritten every time, but only the mapping is to be reworked accordingly so that it is relatively easy to transfer this variant to other systems. Okay, so in this system, as you can see, this is the existing embedded system, and then we have added a microcontroller board which is basically connecting to the cloud. So this microcontroller board can have different kind of interfaces, CAN, UART, WLAN, Ethernet, all these things are available here, so that it can obviously connect to the local area network and then it can send the data to the cloud. So another method is this extension by smart actuators and sensors. Okay, so traditionally the embedded systems usually consist of a control unit, several sensors, actuators which are connected to the control unit are via field buses. Now the control unit assumes the signal processing function in such systems. Should smart sensors and actuators be used now, the sensors take over even the processing of the signal and the actuators independently check their current status and correct it if necessary. So in this kind of implementation, as you can see, we are replacing the sensors and actuators itself. So normal sensors and actuators are replaced by smart sensors and actuators. Okay, so what they do is that the sensors send the data directly to the cloud, and what the actuators do is that they just update their current status from the cloud. So these sensors transmit their data to a central control unit, which is obviously through the field buses. Now in order to extend such a system to cyber physical systems, it would be conceivable to also send data from the sensors and actuators which are sent via the field bus to the cloud and process it there. However, a high data volume is the result here, and the cost of the smart sensors and actuators must not be underestimated. So if you see the previous implementations, we were just adding a module that was connecting to the local area network or to the WLAN in order to connect to the internet, or we were using a different microcontroller board itself or a development board itself. But in this case, as you see, we are replacing the sensors and actuators itself by smart sensors and actuators. So the cost of the system might increase. This is the issue with this kind of method. Now that we have already discussed a lot about the implementations of the cyber physical systems, let us now discuss the CPS or the cyber physical system reference architecture models. So if you want to implement the cyber physical systems, a kind of architecture should be followed. So if it is a standardized architecture, it will be really good, because different manufacturers will be following the same and they will come across solutions which will instantly fit into a industrial environment. So some of the notable initiatives include the platform Industry 4.0 promoting digital transformation in German manufacturing, and the Industrial Internet Consortium or the IIC, which is aimed at accelerating the growth of the industrial internet through collaboration with industry executives. So here, if you go through the different kind of literature that is available on the cyber physical system architectures, you will definitely find these three important reference architectures. The first one is the 5C architecture, then there is RAMI 4.0, and then there is IIRA. So one by one, let us discuss the three architectures. So let us first discuss the 5C architecture. The 5C architecture is a proposal based on automation processes models centered on data acquisition for industrial devices with 5 levels of system operation. So here you can see the 5 levels. So the 5C architecture provides an implementation guide for cyber physical ecosystems, but some basic characteristics were not considered for its application in the Industry 4.0 scenario. It is necessary to consider information flow both vertically as well as horizontally between products and machines, processing them according to client specifications, etc. So if we look into the 5C architecture, services like stock management, load transport requests and purchases can be automated through factory virtualization, leading to Internet of Services, a key pillar of Industry 4.0. In this particular model, we can see these are the different layers. First one is the smart connection, then data to information conversion, cybernetic or the cyber layer as shown here, then the cognition layer followed by the configuration layer. Now let us look at the smart connection layer. So integration of physical devices connected in a communication network is the job of this layer. So sensor network, data acquisition are a part of this particular layer. Then data to information conversion. So conversion from monitored device data to information in order to understand them and apply to the physical world is the job of this particular layer. Then the cyber or the cybernetic layer. Use of information for the device virtualization. It is also the level responsible for the communication among the different assets. Then we have the cognition layer. Functions of monitoring and prognosis for failure prediction and maintenance optimization are its jobs. Similarly, there is a configuration layer. So transmission from virtual to the physical world, making the machine self-adjusting and self-adaptive is its role. Next is the RAMI 4.0. This RAMI 4.0 is a reference architecture model for Industry 4.0 created by Platform Industry 4.0 to define communication structures and common language within the factory, enabling integration of IoT and services in the Industry 4.0 context. So the RAMI 4.0 is a service-oriented architecture that combines IT components to promote horizontal and vertical integration within the factory, connecting products and the cloud. So RAMI 4.0 is represented by a three-dimensional map with three axes, as you can see here. First axis hierarchical levels, second axis product life cycle, and the third axis are the architecture layers. The axis 1, which is, as you can see, is hierarchy levels, focuses on flexible machines and systems, distributed functions and improved communication among all involved participants, treating products as part of the architecture. Similarly, the axis 2, which is product life cycle, describes assets from idea to production, usage, then maintenance, so representing objects with value for an organization such as devices or equipment. So similarly, the axis 3, which is the CPS proposal, it encompasses the architecture layers and focuses on Industry 4.0 components globally and uniquely identifiable objects with communication capacity. The Industry 4.0 includes an asset and administration shell containing relevant information for asset management, representing the physical and digital aspects of a machine, equipment or product. So this administration shell serves as a standardized interface for communication networks, connecting physical entities to Industry 4.0. All the administration shells, that means, are managed by superior system administration shell or SAS, facilitating intercommunication between them. So let us now look into the IRA, or the Industrial Internet Reference Architecture, which is an open architecture developed by the IIC, or the Industrial Internet Consortium, based on the industrial IoT standards, emphasizing interoperability among industries. The IRA is organized into 4 viewpoints. Those are the business viewpoint, usage viewpoint, implementation viewpoint, and the functional viewpoint. So the business viewpoint identifies participants and their business views, values, and objectives in Industry 4.0 systems, or the industrial internet systems. The usage viewpoint describes the IIoT systems or industrial IoT systems expectations to provide the intended business objectives. Similarly, the implementation viewpoint identifies the technologies required to implement the functional component, their communication schemes, and the life cycle procedures. Similarly, if we look at the functional viewpoint focuses on the functional components, their interrelation, interaction with external elements, and is divided into 5 domains. Those are the control, operation, then the information, application, and the business viewpoints. The functional viewpoint also includes cross-cutting functions that enable the main system functions and system characteristics, which are properties or emergent behaviors of the IIRA system. So let us just have a look on the different operations of these components. So first is the control. So functions for industrial control systems, such as the sensor data reading and writing, communication among sensors, actuators, controllers, gateways, and other devices, abstraction of devices through a representation of a virtual entity, interpretation of data collected by sensors and other devices, are its responsibilities. Similarly, if we look at the operations, so functions for prognosis, management, optimization, and monitoring of the system in the control domain are some of its responsibilities. Now, if we look at the information domain, functions for domains data collection and then the data transformation, modeling, and analyzing to acquire high-level system awareness are its responsibilities. Similarly, there is this application domain. So functions capable of implementing application logic while performing specific business functionalities. This domain applies a set of rules with specific functionalities required in considered use cases, and a set of functions whose applications can expose their functionalities to other applications that consume them, or user interfaces for human interactions. These are its responsibilities. Now, one of the most important domains is the business domain. So end-to-end operation of industrial IoT systems, integrating them with specific business functions of traditional or new system types, are its responsibility. Now we'll have a look at the prototype implementation of an Industry 4.0 application for an industrial coffee machine. So here, as you can see, there's an industrial coffee machine. So what we want to do is we want to convert this into a cyber physical system. So obviously we will have to use a method to connect it to the internet. So if you could recall, we had discussed a number of ways of implementation of cyber physical systems, like the direct system extension, system expansion by microcontroller board, then extension by smart actuators and sensors. So basically this second option, that is the system expansion by microcontroller board, has been utilized here. Along with the industrial automation system, you can see another microcontroller board being interfaced, which will be connecting to the cloud. So let me just take you to that slide. Yes, so here you can see that here we have used a microcontroller board which is connecting through the field bus. In this case, the field bus is the CAN. Through this, it is connecting to the industrial coffee machine, and it is getting the different information and sending the same to the cloud. A smartphone which is having some application can be used to remotely control this industrial coffee machine. So let us now summarize what we discussed in this particular class. We also discussed the concept of cyber physical systems which integrate computation, networking, and physical processes. So cyber physical systems involves embedded systems that interact with physical world through sensors, actuators and communication component. It enables the Internet of Things and offers benefits such as remote diagnosis and customization. So these are some of the references I considered while developing the content for this class. I'll just show you a small video of how cyber physical systems can be implemented in Industry 4.0. You can see some pilot cyber physical systems being implemented by a company called Siemens. So based on some commands, the machine is operating, as you can see. Actually, there is a digital twin of every of the robots or physical processes that are going on the server or on the internet. So through the internet, whatever operations we assign to the digital twin, the same will be passed on to the physical process or the physical robot or any physical machine, and it will be just implementing the solution. So many of these applications can help optimize business processes, can make the jobs of workers easier. So this is all about today's lecture.